How to calculate repeatability? Take a sample of 20 patients and take 5 observations per patient in the same setup. Calculate the mean and standard deviation of repeated observations of each patient. You now have 20 means and 20 standard deviations. Take the average of 20 standard deviations and report this figure as repeatability of the system of measurement. What is the basis for 20 patients and 5 observations per patient? The numbers are completely arbitrary. In statistics always, the more, the merrier, if you can manage and afford the cost and time. However, do not take less than 4 observations per patient and less than 10 patients. It is important to report the basis of calculation when you report the repeatability coefficient, that is, the standard deviation, of your study. Repeatability and reproducibility are expressed by standard deviation. Then why do you compute mean? You are correct. Standard deviation alone is sufficient to report repeatability and reproducibility. The mean is needed if you want to study repeatability and reproducibility further. It is more true about repeatability, and hence, for brevity, we drop the term reproducibility. The explanation for reproducibility is similar. Inherent variation in a system of measurement, at times, depends on the measurement itself. The following example makes it clear. Imagine, you plan to purchase a weighing machine, where the manufacturer guarantees that the measurement error lies within plus or minus 5%, and you think you are okay with this. Now, if a child, whose actual weight is 20 kilograms, stands on the machine, the display might show anything between 19 kilograms or 21 kilograms, error equals plus or minus 5% of 20 kilograms equals plus or minus 1 kilogram. But if an adult of 70 kilograms is weighed by the machine, the error magnitude is plus or minus 5% of 70 kilograms or plus or minus 3.5 kilograms. It implies that the inherent variation depends on the mean. As the mean goes up, the inherent variation of the measuring instrument also increases. But this is not desirable. So it is good to study if the error in measurement has any bias or not. How can you identify the bias in your system of measurement? For repeatability, you take repeated measurements under the same conditions but for different objects. You get a pair of mean and standard deviation for each object. Plot the mean along the x-axis and standard deviation along the y-axis. Do you see any pattern in the plot? If yes, then the measurement error is biased, and the system is not reliable. If you do not see any pattern, you can rely on the system if the standard deviation is acceptable to you. This plot has a pattern. Standard deviation increases with mean. The system of measurement is biased. This plot does not have a pattern. The system of measurement is unbiased. It was said earlier that reproducibility cannot be calculated from one study. But some authors reports repeatability as well as reproducibility. How? Reproducibility implies the consistency of a system of measurement under different setups. Those studies that report reproducibility standard deviation actually note observations of the same patients with the same machine but varying operators. Machines can also be varied if the research institute has multiple machines. But most institutions have only one machine, like OCT, it is very expensive after all, and more often, only operators are changed. They are not wrong either. Because, apart from the inherent variation that machine cannot help, the next big sources of variation are the operators. Hence, it is okay if some authors report reproducibility standard deviation just by changing the operators. But it should be mentioned clearly. Some authors report the coefficient of variation along with the standard deviation as measures of repeatability and reproducibility. Does the coefficient of variation give any extra information about the repeatability and reproducibility? Coefficient of variation equals standard deviation divided by mean. But without the mean, the coefficient of variation does not tell us anything. It is not recommended to use coefficient of variation as an indicator of repeatability or reproducibility. In order to examine if the system of measurement has any bias, use plot explained earlier. If the coefficient of variation does not vary object to object, it is an indication of bias. The repeated measurements, taken by us, represent a sample. Hence, the standard deviation reported by us as the measure of repeatability or reproducibility is not absolute. It may vary from one study to another. Usually, when the mean of the variable changes, its standard deviation also changes. So that, the ratio of the standard deviation to the mean of the variable remains more or less constant over time. However, this is only empirical and always not true. And, this ratio has a special name, coefficient of variation. Coefficient of variation equals standard deviation divided by mean. The coefficient of variation has an empirical property, which comes handy in several situations. In many agricultural and social studies, it has been found that the coefficient of variation remains unchanged over time. So, if we have some idea about the coefficient of variation for any previous period, we assume the same value of the coefficient of variation at present. This is based on a simple logic: when mean increases, the variation also increases proportionally. However, this logic is only empirical. There is no mathematical basis for the same. The logic applies in many situations. For example, when per capita income increases, the disparity between the rich and poor also increases. The rich gets richer. The poor does not become poorer per se, but the gap increases even if their income increases at the same rate. Imagine, one earning $10 and another earning $1,000 per day doubled their income in 5 years. So their income becomes $20 and $2,000 respectively. The gap increases from $990 to $1,880. Average income increases, standard deviation also increases. The coefficient of variation remains unchanged. I have a small sample, around 30, for my study. Now if I keep aside part of the sample for repeatability study, my sample size for the main study is reduced further. What should I do? Take multiple measurements for every unit of the sample. Calculate the mean and standard deviation of multiple measurements for each unit. Plot the mean, standard deviation along the x-axis and y-axis, respectively. If you find a pattern, the system is not reliable. Stop. If there is no pattern but the standard deviation is high, the system is also not reliable. Stop. If there is no pattern and the standard deviation is within your acceptable limit, then you can go ahead with the experiment. Take the mean of the multiple measurements for each unit as the measurement corresponding to that unit. You report the average standard deviation of all 30 sampled units as the repeatability standard deviation. For other statistical analyses, consider the means. So, you have calculated repeatability standard deviation from a sample of 30. And you have all 30 units for the main study. How do I know if a repeatability standard deviation of 0.60 good or bad? Short answer. If the repeatability standard deviation is 0.60, then the measurement error lies between plus minus 2 times 0.60 or plus minus 1.20. If a measurement error of plus minus 1.20 is acceptable to you, then you can go ahead with a repeatability standard deviation of 0.60. Deep learning. Repeated measurements of something form a normal probability distribution, that is, a normal population, with some mean and standard deviation. The actual measurement, that is, the value we are looking for, is the mean of the distribution, population mean. This is point number 1. If you draw a random unit from a normal distribution, 95% of the times, it lies between the mean plus minus 1.96 times the standard deviation. Mu is the mean, and S is the standard deviation. Where does 1.96 come from? It refers to the 95% confidence interval of the standard normal distribution. 95% of the times, it lies between the mean plus minus 1.96 times the standard deviation. 90% of the times it lies between mean plus minus 1.64 times the standard deviation. 99% of the times it lies between mean plus minus 2.58 times standard deviation. 95% of the times, a random value, drawn from a normal population, lies between mean plus minus 1.96 times the standard deviation. This is same as saying, if the random value, we have drawn from a normal population, is x, and the standard deviation or s is known, then 95% of the times, the interval between x minus 1.96 times the standard deviation and x plus 1.96 times the standard deviation will include the mean. Note that, 5% of the times, the above interval will not include the mean mu. If it is not intuitively clear, then see the following algebra. X is greater than mu minus 1.96 times the standard deviation, implies that x plus 1.96 times the standard deviation is greater than mu. X is less than mu plus 1.96 times the standard deviation, implies that x minus 1.96 the standard deviation is less than mu. Clubbing them together, we say mu minus 1.96 times the standard deviation, less than x, less than mu plus 1.96 times the standard deviation, implies that x minus 1.96 times the standard deviation is smaller than mu, again less than x plus 1.96 times the standard deviation. What is its implication? Based on the random value, drawn from a normal population, we can give an interval estimate of its mean, which will be correct 95% of the times. 5% of the times we would make an error. Is it clear up to this point? If so, we will take up an example here. Note that S is the same as the repeatability standard deviation. Say we have got S equals 0.60. Then, 1.96 times, S is equal to 1.96 times 0.60 or 1.176. 1.96 is often approximated as 2. 1.176 is rounded off to 1.20. Now, if the observed value of RNFL thickness is 110 micron, the actual value you are looking for lies between 110 plus minus 1.176, that is, between 108.8 and 111.2, with 95% probability. Can you accept an error of this magnitude in your measurement? If your answer is yes, then a repeatability standard deviation of 0.60 is okay for you. If your answer is no, then 0.60 is too high to be acceptable. So you ask yourself, does a measurement error of plus minus 2 times the repeatability standard deviation really matter for your study? If it does not matter, then repeatability standard deviation is good for you. How should we write about repeatability and reproducibility in the text? Declare the results. The repeatability standard deviation of the RNFL thickness, RNFL thickness is the variable, was 0.034 for the normative is a group, and 0.054 for the diseased patients for another group. Write about the sample size and process of calculation. It was based on the measurements in 40 patients, 20 each in the normative and diseased groups, taken in 5 instances of each patient at the same sitting. Follow the same style for the reproducibility standard deviation. The reproducibility standard deviation was 0.67 and 0.87, respectively, for the normative and diseased patients, based on the measurements in 40 patients, 20 each in the normative and diseased groups. For each patient, 5 measurements of the RNFL thickness was taken by 5 different optometrists,